I was imagining we continue to talk about logarithmic functions, exponential functions, and their derivatives and kind of all that jazz. So as usual, if there are things you want to see, questions you have, don't hesitate to ask them. You're more than welcome. I think everyone's probably got it. You can just set that. It's fine. Yeah. So let's go here. And I kind of want to start here. So let's remind ourselves just a couple things we talked about last time. We talked about how the derivative of the natural log of x was equal to 1 over x. Oh, wow. How about focus? Okay. And then we also talked about the more general version of this rule, which is that the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. These are kind of the two, I don't know, I don't want to say most important, but these are the main rules for logarithmic differentiation that I think about. Derivative of natural log of x is 1 over x. Derivative of natural log of some stuff is the chain rule version. It's 1 over the stuff times the derivative of the stuff. So for example, we could find the derivative of the natural log of sine of x. And that's going to be 1 over sine of x times the derivative of sine of x, which we should then keep going in and out of focus here, which is going to end up being 1 over sine of x times cosine of x. And although it's perfectly fine to leave the answer like this, it does bear simplification. We could rewrite this as cosine x over sine of x, which is cotangent of x. Not necessary, but worthwhile. Sorry, I'm trying to keep things in focus here. And this is really kind of, well, it's not it, but this is the starting point for these kinds of problems. If I want to find the derivative of, say, the natural log of x to the 4th plus 1, same idea. Oh, when you have a second, can I see your symptom survey, please? So in fact, why don't you all take this derivative in the same sort of way while I take a sip of water? For 16B, yeah. Come in, and yeah, you can scan the attendance form. You can also fill out the attendance form later if now is not convenient. It's pretty straightforward. So again, derivative of the natural log of some stuff, 1 over the stuff times the derivative of that stuff. Now, usually I would probably just skip writing out the derivative of x to the 4th plus 1 and write it as 1 over x to the 4th plus 1 times 4x cubed. Or you might prefer to write it as 4x cubed over x to the 4th plus 1. Doesn't really matter. This is probably easier to type into WebWork than this, but they're the same thing. Come on in. Can I see your symptom survey, please? So let me remind you all a couple thank you, properties. There are 3 specifically that I want you to remember, which are 1, the log base b of a times b is the log base b of a plus the log base b of b. Or we often say it's the product rule for logs. The log of a product is the log of the first thing plus the log of the second thing. We also have a quotient rule for logarithms. You take the log base b of a divided by b, it's the log base b of a minus the log base b of b. And thirdly, we have the log base b of a to some power is equal to that power times the log base b of a. These are rules we use mostly to either expand or compress logarithmic expressions to make it easier to differentiate them. It's not the only thing we use them for, but in this class, it's kind of the primary thing. So let's look at some examples. Keep my notes in order. So let's say we have the function y equal to the natural log of x to the fourth times cosecant of x divided by e to the 6x times the cube root of x squared plus 1. And I want to find dy dx. Well, before we do that, I really keep going to not focus. Before we do that, we really want to make our lives easier. You could do this the hard way, right? We could do it as 1 over all of that garbage. You shouldn't write this down. You don't want this. But you could do it this way if you really, really felt like you needed to make your life harder. And then multiply it by the derivative of all of this garbage. That seems awful, right? I don't want to do the derivative of this where I have to use the quotient rule and the product rule twice and the chain rule a couple of times. That seems really, really not great. Instead, what we're going to do is simplify first. And this is what I would say is often good advice just in general. If you're differentiating something or fairly soon anti-differentiating something, it is frequently a good idea to try and simplify that expression as much as possible before doing so. So what I really want to do with this y equal to the natural log of x to the fourth times cosecant of x divided by e to the 6x times the cube root of x squared plus 1 is break it up into multiple logarithms. And you can do this in like 3 steps or 1 step, depending on how comfortable you are with it. I'm going to show all the steps, but then I'll kind of talk about how you can do it a faster way. So first, I see a quotient. I see the natural log of something divided by something else. I'm going to write that as the natural log of x to the fourth times cosecant of x minus the natural log of e to the 6x times. I'm going to rewrite the cube root of x squared plus 1 as x squared plus 1 to the 1/3 power. And then I see some logs of products. So I'm going to write this as the natural log of x to the fourth plus the natural log of cosecant of x minus, now I want to be extra careful here. I'm going to have the natural log of e to the 6x plus the natural log of x squared plus 1 to the 1/3. And I wrote brackets around that to remind myself that this minus sign has to distribute to each of those terms. So I'm going to do 2 things at once here. I'm going to bring down all the powers. So this 4th power can come down in front. This 6x can come down in front. This 1/3 can come down in front. So I'm going to have 4 natural log of x plus natural log of cosecant of x minus 6x times natural log of e. And then it's going to be a minus 1/3 natural log of x squared plus 1. And that is as simplified as it gets. Here's what I have observed over the years. When you do this, the factors in the numerator, in this case, the x to the fourth and the cosecant of x, always end up with a positive coefficient. We have a positive 4 natural log of x and a positive natural log of cosecant of x. Whereas the factors in the denominator, e to the 6x and the cube root of x squared plus 1, end up with negative coefficients. So the top things are always positive, the bottom things are always negative. That's how it always ends up working out. So you could jump straight from like here to here. Be like, oh, I know it's going to be the natural log of x to the fourth plus the natural log of cosecant of x minus the natural log of e to the 6x minus the natural log of the cube root of x squared plus 1. And then you can bring the powers down in the next step. Yeah. No. And that stands for the cosecant. So CSC of x is the cosecant of x. And it's equal to, sorry, right in that place you couldn't see it. And cosecant is the reciprocal of sine. Just like secant is the reciprocal of cosine. So now we're finally simplified enough that we can take the derivative. So I'm going to find dy dx or y prime. It doesn't matter. You can write either thing. Y prime, dy dx. There's a lot of ways to write what we need for the derivative. So constant multiples hang out. I'm going to get 4 times the derivative of the natural log of x, which is 1 over x. And I'm going to get, all right, I need to take the derivative of the natural log of some stuff. It's going to be 1 over the stuff times the derivative of the stuff, which we'll figure out in a second. I should have done one thing in the previous step here, which is I should have noted that the natural log of e is 1. So that when I take the derivative of 6x, or I should say minus 6x, I get minus 6. Finally, the derivative of minus 1/3 natural log of x squared plus 1, the minus 1/3 constant hangs out, and the derivative of natural log of some stuff is 1 over the stuff times the derivative of the stuff. And again, I'm writing out kind of a lot of things, but probably if I was doing this on my own, I would have actually just found the derivative of cosecant and the derivative of x squared plus 1 in this step. Question? Oh, so that's a, I would say that's a prime. So that's one notation for the derivative. So what I'm telling myself there is I still have to take the derivative of that piece. I haven't finished the problem just yet. So doing the last couple steps here, make sure everyone can see all the things on the page. If you ever can't see something up there, please just let me know. It's, the space is limited. Same thing goes for you on Zoom. They're pretty matched up, but I feel like the Zoom people have a little bit less visibility. So let me know if something can't be seen. So we're going to get 4 times 1 over x, which I probably should have written as 4 over x. If I could go back in time, I would write that as 4 over x. And then I get 1 over cosecant of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. Minus 6 minus 1/3 times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. So one last thing. Don't worry, I think I know what your question is. But, oh, sorry. Right here? That says negative cosecant of x times cotangent of x. And then if I was simplifying this, I would probably rewrite it as 4 over x. I would cancel a cosecant here and a cosecant here and get minus cotangent of x minus 6 minus 2x over 3 times x squared plus 1. Whenever I taught this class, I would always ask a question like this on an exam, where students needed to expand it out and then take the derivative. It's just a good question.
For the last question you had, not this one.
Mm-hmm. For the derivative of the natural log of x to the 4th plus 1?
The derivative of the natural log of x to the 4th plus 1.
Mm-hmm.
Did you expand that one out?
No, that's an excellent question. We can't. So let me expand on that. Yeah. So the natural log of x to the 4th plus 1 is already as simple as it gets. Oops, you want to see the things. Yeah. Yeah, it's as simplified as possible. And the thing here is when you have addition inside a logarithm, there's kind of nothing you can do with it. So we're stuck. All we can do to take the derivative is just 1 over the stuff times the derivative of the stuff. Yeah, right. It's not multiplied. Whereas, versus, I know 1's not very interesting, but if you had something like y equal to the natural log of, say, like 5x to the 4th, although you don't need to, right? You could totally take the derivative of this as just 1 over the stuff times the stuff, right? It's not like a hard derivative to take. So one way to do this would be to say the derivative is 1 over 5x to the 4th times the derivative of 5x to the 4th, which is 20x cubed. And then you could simplify it if you wanted to. 20x cubed over 5x to the 4th. You can cancel a 5. You can cancel an x cubed. And you get 4 over x. Alternatively, we could have simplified it first. We could have said y is equal to the natural log of 5x to the 4th. That's, I can't bring the power of 4 down yet, because the power has to be kind of on the entire thing to be able to bring it down in front. But what I can do is I can break this up as the natural log of 5 plus the natural log of x to the 4th. And then I can rewrite that as the natural log of 5 plus 4 times the natural log of x. And now I can take the derivative. All right, I'm going to ask you a question. It's not a trick question, but it's a question people often answer incorrectly. What's the derivative of the natural log of 5? 0, right? Because it's a constant. And then the derivative of 4 natural log of x is 4 times 1 over x. So we get the same thing, 4 over x. Either way is perfectly legitimate, but sometimes you'll have things that are much less nice looking than this. And so you really kind of, you don't have to, but it's in your best interest to simplify it as much as possible before differentiating. Yeah.
Why couldn't we get the power down?
So we can definitely do something like this. So the problem is when I write something like 4 times the natural log of 5x, if I wanted to bring that power up, here's what it looks like. It looks like the natural log of 5x to that power. Each part of the 5x is raised to the power. So this would be the natural log of 5 to the 4th times x to the 4th, which is not the same as the natural log of 5x to the 4th. Powers can only come down if they're the power on kind of the entire argument. Other questions about this? Okay. Yeah, let's look at a couple other things concerning logarithms. Specifically, what about the derivative of logarithms with other bases? So far, we've talked about one base and one base only. The natural base. And now I know I didn't write it, but what is the base of that logarithm there? Everyone's favorite number, e. Second favorite number, e, right? It's e, right? But what if I want to find, say, the derivative of log base 4 of x? Well, there's a not too terrible way to do it. The not too terrible way to do it is to use the change of base formula. So there is a formula for logarithms that says if you have the log base b of x, you can change the base. You can make it whatever base you want. The base we want is the natural base. We always prefer log base e. That is the best base, or it's the best for calculus. So we can rewrite this as the natural log of x divided by the natural log of b. I'm happy to talk more about where that formula comes from if anyone wants to see it, but if everyone's cool with it, I'll move on. But really, like, if anyone's like, I don't remember where that formula comes from, that's totally fine. I feel like I'm going to say it anyway, because just a reminder. So where does this come from? It's because if you're trying to rewrite this, let's say this is equal to y. Well, there's a way of rewriting this exponential equation. So sorry, this logarithmic equation as an exponential equation. I can rewrite this as my base to the y power equal to x. The thing I always keep in mind when I'm doing this is, oh yeah, remember, log base 2 of 8 equals 3 is equivalent to 2 to the third equals 8. That is always the equation that I'm remembering in my head. Oh yeah, log base 2 of 8 equals 3, because when you're finding the logarithm, you're finding the power you raise the base to equal the number you're taking the log of. So that's the same thing here. And then I'm going to take the natural log of both sides. Or whatever base you want to. You could do log base 10, you could use log base 3, whatever base is convenient. But we're using the natural base because that's the one that's convenient. And then this power gets to come down. So y times the natural log of b equals the natural log of x. And finally, y equals the natural log of x divided by the natural log of b. But y was the log base b of x. So that's where that change of base formula is actually coming from. Great. Well, if I want to take the derivative of the log base 4 of x, I'm going to rewrite it as the derivative of the natural log of x divided by the natural log of 4. And the great thing here is I don't need to use the quotient rule. That's really just the derivative of a constant 1 over natural log of 4 times the natural log of x. And when you have constant multiples, they just hang out. So the derivative of a constant times this is just the constant times the derivative of the natural log of x, which is 1 over x. And the way we kind of typically write this is 1 over x natural log of 4. And we can, well, actually, let's look at a different example before we kind of go on here. Let's look at another example. Let's say I want to find the derivative of the log base 7 of x to the 6 plus 3. I'm going to do the same thing. I'm going to use a change of base formula. So I'm going to rewrite this as the derivative of the natural log of x to the 6 plus 3 divided by the natural log of 7. And although you don't have to rewrite it, I'd really like to write it as a constant times a function. To me, it's just easier to see what to do. So I really prefer to rewrite this as the derivative of 1 over natural log of 7 times the natural log of x to the 6 plus 3. Because then it's much more obvious to you that, oh yeah, that's a constant. And so when I differentiate, I'm going to get that constant just hanging out times, okay, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And you could leave it like this, or you could make it quote unquote more condensed by writing as 6x to the 5th over the natural log of 7 times x to the 6 plus 3. Either way, totally fine. We can generalize this to a rule, right? So you could do this every time where you use the change of basis to rewrite a log with a different base, but it always ends up being the following thing, that when you find the derivative of the log base b of x, it ends up being 1 over x times the natural log of your base. And if you're taking the derivative of the log base b of some stuff, it ends up being 1 over your stuff times the natural log of your base times the derivative of your stuff. Or if you prefer, the derivative of your stuff divided by your stuff times the natural log of your base. So they're really just the same rules as before with logarithms. The only additional thing we have to remember is that you also have to divide by the natural log of this different base. It would also work if your base was e, because the natural log of e is just 1. I should point out, I like writing like this because to me, literally this is how I say it in my brain, right? I'm not saying the log of f of x or the log base b of u or whatever. I'm saying I've got the log base b of some stuff, and the derivative is 1 over the stuff times the derivative of the stuff times 1 over natural log of b, or divided by natural log of b, whichever way you want to say it. But just so you are aware, if you were seeing this in a textbook, it would probably look more like the derivative of log base b of u, where u is some function of x, is 1 over u times the natural log of b times du. That's how a book would probably write it. 1 over the stuff, natural log of the base, times the derivative of the stuff. I just don't want you to see this later on and be like, that looks way different. It's the same thing, it's just using more mathy notation. Questions?
So is the first one the natural log of base b of x? Is that 1 over x times the natural log of b? Is that it stop there and it doesn't have the derivative of x?
Well, you could, both things are correct, meaning you could stop there, or you could say times the derivative of x. Because what's the derivative of x?
1.
Right. So multiplying by 1 can keep it the same.
But why couldn't you do the same thing for class?
For which one? For this one here?
Yeah.
Well,
the derivative of u be 1 as well.
No. So the thing is, so that's a really kind of good question. The idea here is that we are making the assumption that, right, it's really u is exactly, you said it best. U is some stuff. U is a function of x. So we're trying to save space, but really like, this is actually how it gets written, but you could write it the longer way as the derivative of log base b of this function u of x is 1 over u of x times natural log of b times, you could write it as du dx or as u prime of x. Same idea. But really, right, the rule is just 1 over the stuff, natural log of the base times the derivative of the stuff. So I think it's, okay, question.
Why did we not get the derivative of 1 over ln of 7?
So one more time.
Why did we not get the derivative of 1 over ln of 7?
Well, so let's take a look at that for just a second. So it's a good question. If I look at this here, if I take the derivative of 1 over natural log of 7 times the natural log of x to the 6 plus 3. One way I could do this is by using the product rule. All right, I've got a product. I've got a, if you want, I've got an f times a g. And so when I take the derivative, I'm going to get f prime times my g plus f times my g prime. All right, what's the derivative of this 1 over natural log of 7? It's not 1. It's 0 because it's a constant, right? There's no variables there. So if you look at a thing and you don't see x or whatever variable you differentiate with respect to, you got to think, oh, that's a constant, right? I don't have any variability there. It's always going to be. Now, I don't know what this number is. It's 1 over some decimal thing, but it's something that never changes. So that derivative is 0. And then I have, it doesn't really matter that that's natural log of x to the 6 plus 3 because this whole piece is 0. And then my f is 1 over the natural log of 7, and then the derivative of g is going to be 1 over the stuff times the derivative of the stuff. Same thing up there. But what we're really using is what's called the constant multiple rule, where if you have the derivative of a constant times your function, it's equal to the constant times the derivative of the function. It's just that we kind of sometimes get a little tricked up by the fact that 1 over natural log of 7 kind of feels like it shouldn't be a constant. It kind of looks like it could be a function, but it's not, right? It's just a constant. And what I want to do is kind of write down for you all a somewhat exhaustive list. It's short, it's not like super long, of the logarithmic and exponential derivative rules. So we just covered all the logarithmic ones. And here they are kind of in the order I think of them in. The derivative of the natural log of x. I know we like kind of just wrote these down, but they make sense. Is 1 over x. And the derivative of log with a different base, say log base b of x, is 1 over x natural log of b. And then we have the chain rule versions. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Which you could totally put that derivative of the stuff in the numerator if that looks better to you. I don't like to, just because I feel like it's easy. When I say it this way, it really reminds me that the chain rule is what's happening here. I do 1 over the thing, and then I multiply by the derivative of the thing. And then finally, the chain rule version for a different base. So the derivative of log base b of some stuff is 1 over the stuff times 1 over the natural log of the base times the derivative of the stuff. Now let's cycle back a little bit. I know it's almost a whole week ago, last Thursday, to our exponential derivatives and remind ourselves, because there's a very kind of similar pattern at play here. I know it's been a little while, but I'll remind you all that the derivative of e to the x is e to the x. And then the derivative of b to the x, well, here's a nice thing. And I think we'll revisit this again because I feel like you all might not remember. The derivative of b to the x is b to the x times the natural log of b. Okay, let's take a look at that, because I feel like everyone's like, I don't remember. I definitely did talk about it last Thursday, but not everyone probably saw that. That's all right. So we'll finish this list here in a second with the chain rule versions of these things, but let's go look at some examples. So what if I want to find the derivative of y equals 4 to the x? There are at least 2 ways of doing this. Let me show you one of them. Which one do I want to show you? I want to show you the one I like better, to be honest. So one way of doing this is to take the natural log of both sides. The natural log of y equals the natural log of 4 to the x. And the whole reason for taking the natural log of both sides is to bring down the exponent out of the power, bring down the x out of the exponent. So I'm going to rewrite this as the natural log of y equal to x times natural log of 4. And now we're going to differentiate both sides. So let me ask everybody, what's the derivative of the natural log of some stuff? You don't have to say it, but you should think about what it is. So we're differentiating both sides, and the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Are there questions about that? Right, it's implicit, right? You can write 1 over y times y prime if you prefer. but it's the whole idea, right? We know, right? We know y is a function of x. There's nothing implicit about it. It's very explicitly a function of x, but we're not writing that here. So we're saying, oh yeah, the natural log of this function of x is 1 over my function times the derivative of my function. All right, how about the derivative of x times natural log of 4? Right, I have a constant times a function. The constant hangs out. We multiply by the derivative of x, which is just 1. We're almost done. Solve for the derivative. So multiply both sides by y and get dy dx equal to y times the natural log of 4. And now the last thing we have to do is replace y with what it's equal to. So there's my y. So the derivative here is equal to 4 to the x times the natural log of 4. Totally works. And it works whether your exponent is simple or complicated, meaning your exponent could be x, but your exponent could be, say, I don't know, we have something like 6 to the x to the 5th power. And we could use the same sort of process. Taking the natural log of both sides. Using the rules of logarithms to bring down the power. So the natural log of y equals x to the 5th times the natural log of 6. Then taking the derivative of both sides, again, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. The derivative of x to the 5th times a constant is 5x to the 4th times that same constant. Questions at this point before we finish it? All right, what should I do next? What am I trying to find? Right, so what do I need to do to find y prime? I need to multiply by y. So I'm gonna get y prime equal to y times 5x to the 4th, sorry, times the natural log of 6. And then finally, replacing y with 6 to the x to the 5th, y prime equals 6 to the x to the 5th times 5x to the 4th times the natural log of 6. Or the way I would think of this in general is the derivative of 6 to some stuff is 6 to the stuff times the derivative of the stuff times the natural log of 6. The derivative of 4 to the stuff, sorry, you can't see that. The derivative of 4 to the stuff is 4 to the stuff times the natural log of 4 times the derivative of the stuff, but the derivative of x is just 1. So this definitely implies a rule. This implies that we can say that the derivative of some base to the stuff is that base to the stuff times the derivative of the stuff times the natural log of that base. Now, there is a totally other way of doing this. You don't have to do it this way. You can do it that way. But let's go back to what we were writing down before and write these down before we get too carried away. So just to revisit our rules of differentiation for exponentiation and logarithms is we know the derivative of e to the x is e to the x. And the chain rule version is the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And finally, the chain rule version where your base is a different base than e, the derivative of b to the stuff is exactly b to the stuff times the derivative of the stuff times the natural log of b. And what I have noticed over, noticing right now, noticing over the years, is that essentially, if you have an exponential thing with a different base, you end up multiplying by the natural log of that base. So if I have b to the x or b to the stuff, I take the derivative, I end up multiplying by a natural log of b. On the other hand, if I have a logarithm with a different base, log base b of x or log base b of some stuff, I don't multiply by the natural log of b. I end up having a division by the natural log of b. So essentially, whenever you have a base other than e, we either end up multiplying by the natural log of that base when we take the derivative, or dividing by the natural log of the base when we take the derivative. Just depends on if it's exponential or logarithmic function. What time is it? Okay. Yeah. Yes. This one, right?
Yeah, y equals 6 to the x to the fifth.
Mm-hmm.
Why do we bring in the natural log for this one? We wouldn't bring it in for something like this one question from class after x equals 4 times e to the x squared.
So I would say you could bring in the natural log there. The idea, though, is that we're kind of using these examples to develop a rule, right? So we could do this every time. I don't want to do it every time. What I really want to do is I want to remember this rule, which is that if I have the derivative of some base to the stuff, I'm going to get the base to the stuff times the stuff times the natural log of b. So for example, or to kind of address that specific example, if I wanted to find the derivative of 4 was e to the x squared. So one way I could do this would be to say, well, first of all, that constant multiple is going to hang out. So it's going to be equal to 4 times the derivative of e to the x squared. And either I could use the rule I've developed. Okay, we've talked about how the derivative of e to the stuff is e to the stuff times the derivative of the stuff. That totally would work. And that's going to be the fastest way to do it after we get comfortable with being like, oh yeah, I know this rule in and out, back and forwards. But we could have also said, could have been like, well, if I want to find the derivative, now it's kind of hard to do it with 4 e to the x squared. I'm going to kind of cheat a little bit and say, I want to find the derivative of e to the x squared. And then I could take the natural log of both sides. And then the natural log of e to the x squared. What is the natural log of e to the x squared? X squared. X squared times natural log of e, if you really want to say it the long way, but natural log of e is 1. More generally, the natural log of e to the stuff is just the stuff, right? That's the inverse property of logarithms and exponentials, which I suppose we could write down in a second here. And then we could do the chain rule thing, or I'm sorry, the implicit differentiation. Derivative of natural log of y is 1 over y times y prime. The derivative of x squared is 2x. And then we can solve for y prime. And then we can replace y with what it's equal to. And y is e to the x squared. So then this ends up being, oh yeah, that's 4 times the derivative of e to the x squared is e to the x squared times 2x. So this process is always valid. It's just that we don't always want to do it. Good. Sorry, so there is a totally other way of doing this, which is still essentially the same, but a little bit. So I really should show you one more thing like this. So let's say we wanted to find the derivative of, let's say we had y equal to, let's make it fun, 5 to the x to the 4th. Now, let's actually just say what, in fact, I'll give you 30 seconds, write down the derivative, find the derivative, using the rules, not like this whole long process thing. Okay, on the clock. You guys on Zoom too, if you want, you can write your answers in the chat if you want to. Write an answer in the chat. I know the Zoom is not particularly interactive because of how I teach, but you can write things. It's all right. My wife's not around to tell me not to do it, so. All right, it's been 30 seconds. So I've got 5 to the stuff. The derivative is 5 to the stuff. What do I have to multiply by? Okay, what else do I have to multiply by?
1 over the stuff.
Not 1 over the, that would be for logarithms. So if I had the natural log of some stuff, the derivative would be 1 over the stuff. But since this is an exponential, right, we need to also multiply by the natural log of 5. So just to contrast this, if we were taking, if our function was y equal to say like log base 5 of x to the 4th, I could find my derivative as 1 over the stuff times the derivative of the stuff, and then a 1 over the natural log of 5. So this is definitely the way I would encourage you all to do this, right? Where you don't have to write a bunch of stuff. I mean, you are in essence remembering a rule, right? Some rules you really just do want to memorize. But another way you could approach this if you were doing it for the first time kind of is, instead of taking the natural log of both sides like we have been doing, you could rewrite this side here. You could, in fact, we could use our inverse properties of logs and exponentials. What are those properties? They're the properties that say e to the natural log of some stuff is just the stuff, and the natural log of e to the stuff is just the stuff. Or more normal people might write it as e to the natural log of x equals x, and the natural log of e to the x equals x. Who wants to be normal? That's not fun, right? So the whole idea is that the exponential function e to the whatever and the logarithmic function natural log of whatever, they undo each other, right? When you compose them together, you get what is in the inside. Some people like to say they cancel out. I avoid using those words because it's really more of an undoing than a canceling, right? It's not like you have 5 over 5 and they cancel. It's like you have e to the natural log of 2 and that just ends up equaling 2. So I hesitate to use the words cancel, but if you want to think of it that way, it's probably not too detrimental. So what we're going to do is we're going to rewrite our stuff 5 to the x to the 4th as e to the natural log of that stuff. So I'm going to rewrite 5 to the x to the 4th as e to the natural log of 5 to the x to the 4th. I will admit, when I learned how to take these derivatives and when I taught this for many, many, many years, I had never seen doing it this way. It was like maybe last year or 2 years ago where some teacher taught it this. I was like, oh, that's a different way of doing it. I don't know if I like it, but it totally works. And some people might really like it. So I feel like I should show it to you. So what we're going to do with this is we're going to use our rules of logarithms and bring down this x to the 4th. So look what I have now. I have y equal to e to the x to the 4th times the natural log of 5. Or as I would maybe think of it, I have e to the stuff. And we know how to take the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. All right, I feel like we've seen it enough times now to know that the derivative of x to the 4th times natural log of 5 is going to be what? Well, the derivative of natural log of 5 is 0, but I have a function times natural log of 5. So I'm going to end up getting the derivative of that times that constant. So we're going to get e to the x to the 4th times natural log of 5 times 4x cubed times natural log of 5. Right, so right, constant multiples, I should say, and it's a really important distinction, right? The derivative of the natural log of 5 plus x cubed, that's going to be 0 plus 3x squared, right? Because derivative of a constant, definitely 0. But if you have the derivative of the natural log of 5 times x cubed, then you're going to get the natural log of 5 times 3x squared, because constant multiples hang out or stick around. I always say hang out. That's just the way I like to say it. I think they hang out. So I would point out our answer doesn't quite look the same as our other answer. Right? Up here, when we took the derivative, we got 5 to the x to the 4th times 4x cubed times natural log of 5. Here we've got this times 4x cubed times natural log of 5. But they are the same, because if you recall, we changed 5x to the 4th into e to the natural log of 5x to the 4th. I should say, sorry. I'm saying 5x to the 4th. I should be saying 5 to the x to the 4th. We changed 5 to the x to the 4th into e to the natural log of 5 to the x to the 4th, which became e to the x to the 4th times natural log of 5. So this here, this really is 5 to the x to the 4th. So this is another way of doing it. I will tell you, I am not in love with it, but some people really prefer to do it this way. Now, the real answer is, or I should say, the real piece of advice I would give is you should memorize these rules. Right? You should definitely, there you go, I put them in here somewhere. Here. You definitely want to remember that the derivative of b to the stuff is b to the stuff times the derivative of stuff times natural log of b. That's going to be the fastest way to deal with these. Okay. So then, oh, do you want to take a picture of that? I also do post the notes on the Google Drive, which is linked from Canvas. So if there's ever something that I've written down that you didn't quite get, it'll be there shortly after class, at least definitely on the same day, if not right after. But you're also welcome to take pictures. All right, so now kind of maybe the real reason I've been talking about both of these methods is sometimes there is a type of function where there is a terrible rule that I've never memorized because it's just not worth it. So what if I wanted to say take the derivative of y equal to, I don't know, x to the sine of x, which I call a function to a function. There were some other things that were on my mind. Okay, we got time. Yeah, I just remember I was looking at the homework assignments. So there's a few kind of things. There's a few topics like this, and yeah, after this we'll definitely kind of move a little bit in a different direction. So to do this sort of problem, you really do have to do one of the two things we've done before, where you either take the natural log of both sides, which is the way I'm going to do it, or rewrite it as e to the natural log of whatever. It's definitely better to take the natural log of both sides. In my very biased opinion, right? I'm totally biased. I like doing it one way. I don't like doing it the other way. So how to do this? We're going to use what's called logarithmic differentiation, which is the thing we've already been doing. This is just a name for take the logarithm of both sides, do the derivative, et cetera, et cetera, et cetera. Yeah. So I'm going to write the natural log of y equals the natural log of x to the sine of x. And then, again, the reason we're taking the logarithm of both sides is to get that thing out of the exponent. I don't want sine of x as a power. It's problematic. But if I rewrite this as the natural log of y equal to sine of x times the natural log of x, now that's something I'm able to differentiate. So now we're going to take the derivative of both sides. As is typical, the derivative of the natural log of y is 1 over y times the derivative of y, or 1 over the stuff times the derivative of the stuff. Unlike before, now on the right-hand side, we actually do have a product of two functions, right? We don't have a constant times a function. We have sine of x, a function, times natural log of x, another function. So we're going to have to use the product rule. So the derivative here is going to be cosine of x times the natural log of x plus sine of x times 1 over x. Right, just to make it, thinking of that as f, and that's g. Little product rule. You can do this last part in one step or two. I'm going to show it in two, but I would usually do it in one. So the last step, we're going to solve for y prime. So we get y prime equal to y times all that. You might simplify that. There's really not much simplifying to do. I'm going to write it as cosine of x times natural log of x plus, I'm going to rewrite this as sine x over x. But the last thing I do have to do is I need to replace y with what it is equal to. If you start off with y as a function of x, right? It's not like some weird implicit thing where you've got x's and y's jumbled together. We should always be able to write our derivative as a function of x. So having a y in there for this particular problem is problematic. We need to be like, oh yeah, our derivative is actually x to the sine of x times cosine of x times natural log of x plus sine x over x. There's our final derivative. There is some bizarre rule that I've seen printed in a book one time. You can't memorize. You shouldn't memorize rule. You should do this way. It is this process is pretty standard. Question. We'll do one more. But any questions about this one in particular? One question people sometimes ask, which I just want to make sure it's okay if you're thinking this, but also okay if you're not. Sometimes people are like, James, isn't sine of x over x equal to 1? And like, you're probably thinking of the fact that the limit as x goes to 0 of sine of x over x is equal to 1. So I just want to clarify, this isn't 1. It's a lot of different values depending on what x is, but this limit from way back in 16a, that limit is 1. But since there's no limit here, that's just sine x over x. All right, let's look at one more example of this. Say we wanted to find, I don't know. Yeah, sure. Let's do y equal to tangent of x to the x cubed power. In fact, I would like you all to try and do that on your own. So start with the same sort of, I'm trying to make it so you can see all the things. Yeah, that works, right? You can see it. Sure. Yeah. So it's really the same process. You're going to take the natural log of both sides, bring it down, derivative, et cetera, et cetera. I'll give you a couple minutes to work on that. All right. I think let's see what we've got here. So again, very similar process. We're going to take the natural log of both sides. And the whole reason for this first step is so that that x cubed can come down. So we get the natural log of y equal to x cubed times the natural log of tangent of x. Now we're ready to differentiate. So 1 over y times y prime equals, okay, product rule over here. 3x squared times the natural log of tangent of x plus x cubed times the derivative of the natural log of some stuff. It's going to be 1 over the stuff times the derivative of the stuff. 1 over tangent x times secant squared of x. And then I think at this point, the last step, really you only need one more step. I'm going to multiply both sides by y, but I'm also going to replace y with what it is. So I'm going to get y prime equal to y times all that stuff. 3x squared times natural log of tangent of x plus, I would probably rewrite this as x cubed secant squared of x over tangent of x. That's it. That's your answer. It's kind of gnarly, but that's it. I will also just, I'm not going to do it, but I will mention if one preferred, you could write the following: y equal to tangent of x to the x cubed. You could rewrite this as y equal to e to the natural log of tangent of x to the x cubed, and then rewrite that as y equal to e to the x cubed times the natural log of tangent of x. And then you could take the derivative of that by finding the derivative as e to the stuff. So the derivative would be e to the stuff times the derivative of the stuff. So you could say that y prime is e to the stuff times the derivative of the stuff. And I will point out that that's exactly, oops, derivative of the stuff. So that's exactly what we have up here, right? This piece here is this piece here. And the derivative of this is exactly this, right? That's what we did. We did the derivative of x cubed natural log of tangent x to get that part there. So you could do it either way. I don't particularly love doing it this way, but if you wanted to do it that way, you should. All right. We got 15-ish minutes, maybe a little more. All the clocks here are like this one says 12:03, that one says 10:06, my watch says 10:07, my computer's right, they're all over the place. So let's look at this. Let's say we have, sure, f of x is e to the -4 over x to the 5th, and we want to find the equation of the line tangent to f of x at x equal to 1. Okay, so we need two things. We need a point and we need a slope. We have half a point, meaning we have the x coordinate. We need the y coordinate. Well, the y coordinate's not too terrible to find. The y coordinate's just going to be whatever f of 1 is, which is e to the -4 over 1 to the 5th, which is just e to the -4. So our point is 1 comma e to the -4. The slope, a little bit more work. We find the slope by finding the derivative. So to find our slope, we're going to find f prime of x. So I probably should have done some legwork instead of writing f prime of x. I really don't want to write -4 over x to the 5th because I really don't want to use the quotient rule. What I would really rather do is rewrite this as e to the negative 4 times x to the negative 5th. That's going to be a much nicer thing to deal with. Yeah, question. Of the line tangent to f of x. Sorry, no, don't apologize. I know my writing is not always excellent. If something's unclear, please don't hesitate to ask for clarification. I know I can look at it and I'm like, oh yeah, that's hard to read. So I really want to think of my function as e to the negative 4 times x to the negative 5th. So then when I take the derivative, I can just use my nice rules for the derivative e to the something. The derivative e to the stuff is e to the stuff times the derivative of the stuff, which is going to be, let's see, that's going to be e to the negative 4 x to the negative 5th times the derivative of negative 4 x to the negative 5th is 20 x to the negative 6th. And there's honestly no good reason to simplify this yet. There might be in a minute. I don't want to simplify this because I only need to find the slope at a particular point. And maybe just plugging in 1 is going to be easy without having to do any extra work. So my slope is going to be f prime of 1, which is going to be e to the negative 4. Okay, I could write times 1 to the negative 5th, but 1 to any power is 1, and multiplying by 1 doesn't change anything. So e to the negative 4 times 1 to the negative 5th is just e to the negative 4. And in a similar way, 20 times 1 to the negative 6th is just going to be 20. Because 1 to any power is 1, and 1 times anything else is whatever else you had. And then I would probably rewrite this as 20 divided by e to the positive 4th. Mostly out of preference, not for any good reason. All right, now I have all the pieces. Once you have the slope and a point, you can use the point slope formula, which, in case you don't remember, the point slope formula is just y minus your y coordinate equals your slope times x minus your x coordinate. So here I would do y minus e to the negative 4th equals my slope, oops, 20 over e to the 4th, sorry, times x minus my x coordinate, which is 1. A lot of the time it's okay to leave it like this, but if you're finding an equation of a tangent line and you're entering it in the web work, often you're going to have to solve for y. So we're going to rewrite this as y equal to 20 over e to the 4th times x minus 1 plus e to the 4th. Sorry, e to the negative 4th. I, again, would probably opt to leave it like this, but sometimes they really want you to find like the slope and the y-intercept. So if you need to write it in slope-intercept form, we actually have to multiply it out and say, okay, I'm going to have y equal to 20 over e to the 4th x minus 20 over e to the 4th. And I suppose it might make sense to write this as 1 over e to the 4th, so I can simplify this to negative 19 over e to the 4th. So my slope is 20 over e to the 4th. My y-intercept is negative 19 over e to the 4th. Kind of funky. Let's look at a slightly different example. So sometimes tangent lines are not too terrible. Find the derivative, that's your slope, find the point, use the thing. But sometimes we have equations where finding the derivative is a little more challenging, like the following. Let's say we had the equation, I don't know. Oh, yeah. No, not at all. Oh, maybe you'd like to see it though. Is there anything I can clarify? I'm sorry, say that one more time. Oh, yeah. Y, that's the y-intercept. Yes, y int. And the only reason I'm pointing, so usually I would just write the equation of the line, but sometimes when I work, they specifically be like, what's the slope? Give them the slope. What's the y-intercept? Give them the y-intercept. So they want to ask you to write it in this way without actually having to make you write it in this way. So they ask you for the y-intercept and the slope instead of asking you to write it in the slope-intercept form. Because Weber will kind of take anything as long as it's right? You can write something very unsimplified, but if they specifically wanted you to write it this way, they kind of have to ask you, okay, what's the slope? What's the y-intercept? You're welcome. So what if instead we had something like this? So the equation, let's say it's e to the x squared y plus x to the fourth minus y to the fourth equals e. So that equation implicitly defines a graph. One cool thing, like technology is great. As a student, I never would have been able to graph this or even see what its graph looked like because it's probably super weird looking. But you can actually totally use Desmos and graph things like this. So not that you need to, right? We don't need to know what the graph of this looks like, but if you wanted to see it, you certainly could. And I think it's worthwhile to see what these things look like sometimes. So I would encourage you later on to go graph this thing and then also graph the tangent line that we're going to find. So this graph has a tangent line at the point 1, 1. We want to find its equation. And I will point out that 1, 1 is a point on this graph. If you plug in 1 for x and 1 for y, it's true that e to the 1 plus 1 minus 1 is equal to e. It should be a point on the graph. Otherwise, it doesn't make sense to ask about its equation with tangent line. So again, we need two things. We already have one of them. We have the point. It's 1, 1. We need the slope. And just like before, we're going to find the slope by finding the derivative. But in this case, we have to use implicit differentiation to find the derivative. So again, with implicit, we're always making the implied assumption that y is a function of x. Even if that's not like 100% true, it's true enough that we're going to do it. So I'm going to take the derivative of e to the x squared y. So we're going to differentiate both sides. All right, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So I'm going to get e to the x squared y times the derivative of x squared y plus the derivative of x to the fourth is 4x cubed minus, all right, this is the part where things have a little bit extra. The derivative of y to the fourth is
y to the third, 4y to the third times y.
Exactly, times y prime. Or as I would say it in my head, the derivative of some stuff to the fourth power is 4 times my stuff cubed times the derivative of my stuff. And then finally, the derivative of e is, yeah, thanks. Okay, now I didn't do all my differentiating because I still have to differentiate x squared y. So I'm going to have e to the x squared y times, all right, I'm going to use the product rule here. We get 2x times y plus x squared times, right. The derivative of y is the derivative of y, which is y prime. Plus 4x cubed minus 4y cubed, y prime equals 0. All right, so there's two different directions to go here. If someone had said, what's the derivative of this thing? And didn't say like find the equation of a tangent line, then we'd actually have to solve for y prime. But since they said find the equation of a tangent line at the point 1, 1, we only need to find the slope when x is 1 and when y is 1.
Real quickly, in the beginning of that equation, when you're multiplying e to the x squared y times x squared y prime, is that because of the chain rule?
Yes, exactly. It's because the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So for this one, since we don't need to know the derivative everywhere, we only need to know at the 1.11, we can plug in 1 right now. And usually that's going to be an algebraically easier thing to solve. So you could totally like multiply this out, group all your y primes together, all your not y primes together, factor out, solve for y prime. But what I'm going to actually do is plug in 1 right now. And that's usually what you want to do if you're specifically trying to find the slope of the tangent line, is plug in as soon as you have taken the derivative of both sides. So I'm going to get e to the 1 times 2 times 1 times 1 plus 1 times y prime plus 4 times 1 cubed minus 4 times 1 cubed times y prime equal to 0. And now I'm going to solve for y prime. So let's see. Simplifying this, right? And so really, if you were doing this, you probably would have just said, James, we have e times 2 plus y prime plus 4 minus 4y prime equal to 0. And now we're going to group our y primes together. Well, actually, now I'm going to distribute this e here. So I'm going to have 2e plus e times y prime plus 4 minus 4y prime equal to 0. I'm going to bring my y primes to the right, atypically maybe. So on the left, I'm going to have 2e plus 4. On the right, I'm going to have positive 4y prime minus e times y prime. I'm going to factor out the y prime. So I'm left with y prime times 4 minus e. And finally, I'm going to divide by 4 minus e. You get y prime equal to 2e plus 4 divided by 4 minus e. That's my slope. And then we need to write the equation, which I think I'm going to maybe run out of room for. We can try. So my equation of my tangent line is going to be y minus the y coordinate equal to the slope times x minus the x coordinate. And unless I had a good reason to, I would leave it like that. I would not try to do anything more with that. I would leave it like that. This is 10:20, so I should stop.